In the previous section, we showed that the electric potential around a point charge Q is given by the following. This means the potential has the same value in every direction at a distance r from the charge. In 3 dimensions, this constitutes a surface of constant potential called an equipotential surface. And thus, for point charges, the equipotential surfaces are an infinite number of concentric spherical shells of constant potential centered around the charge. As we saw earlier, the work done on a charge by an electrostatic force in moving from point A to point B depends on the change in voltage between those points. However, if the charge is moving along an equipotential surface, then the voltage doesn't change. VA equals VB, and the work done is equal to 0. This leads to the following important concept. The net electric force does no work on a charge as it moves on an equipotential surface. Work is done only when a charge moves between equipotential surfaces and therefore moves between different potentials. Consider now what the electric field lines look like for our positive point charge. We know that they point everywhere radially away from the charge. Therefore, the electric field lines pass through the equipotential surfaces and are everywhere perpendicular to them. This perpendicular relationship is valid for all equipotential surfaces and electric field lines, not just for spherical surfaces around point charges. More complicated charge distributions, like an electric dipole for example, have a more complicated set of electric field lines, as the figure shows. However, knowing that the equipotential surfaces must be everywhere perpendicular to the electric field lines allows us to draw in the equipotential surfaces quite easily. Since the potential decreases as the distance from the charge increases, the electric field lines point in the direction of decreasing potential. More specifically, equipotential surfaces and electric field lines have the following characteristic. The electric field created by any charge or group of charges is everywhere perpendicular to the associated equipotential surfaces and points in the direction of decreasing potential. The fact that no work is done on a charge as it moves along an equipotential surface provides an explanation for why the electric field has to be everywhere perpendicular to the surface. As the figure shows, if the electric field was not perpendicular to the surface, then there would be a component of the electric field parallel to the surface, which would apply a force to the charge on the surface and do work on that charge. If work is done, then the potential must change, but that can't happen on an equipotential surface. We have shown previously that the electric field at the surface of a conductor is perpendicular to the surface at equilibrium under electrostatic conditions. Therefore, the surface of a conductor is an equipotential surface. Now we want to show that there is a quantitative relationship between the electric field and equipotential surfaces. Consider the parallel plate capacitor. We know a uniform electric field exists between the plates and points from the positive plate to the negative one. We could ask the following question. What do the equipotential surfaces look like between the plates? Knowing that they have to be everywhere perpendicular to the electric field lines, the equipotential surfaces will be composed of an infinite set of parallel planes, where each plane is at a constant potential. Consider point A on the positive plate and point B on the negative plate. The potential difference between the plates, delta V, is given by the following. The work done in moving a positive charge from point A to point B is equal to F times delta S, where F is the constant electrostatic force acting on the charge and delta S is the distance between the plates. Thus, the work becomes Q times E times delta S. Therefore, the potential difference between the plates of the capacitor can be written in the following way. The quantity delta V over delta S is referred to as the potential gradient, and it has units of volts per meter. In Chapter 18, we showed that the units of the electric field were newtons per coulomb, and now we show that a newton per coulomb is equivalent to a volt per meter. In general, the relationship above gives the component of the electric field along the displacement delta S, where the potential changes from place to place, and this can be applied to a wide variety of situations. For the parallel plate capacitor, if the potential difference between the plates is 5 volts, it is customary to say the voltage of the capacitor is 5 volts. In addition, we often represent the distance between the plates delta S as D, so that the electric field is equal to V over D for the parallel plate capacitor.